Hi everyone, welcome to the AstroLaunch podcast. I'm your host Amy, and today I'm thrilled to welcome. Hi Dr. Dixit, welcome to the podcast. It's so good to have you here.
Thanks, Amy. It's a pleasure.
So, to start off, can you please tell us a little bit about yourself and your job?
All right, I'm a PhD in material science and I work as Director of Engineering at Plasma Technology Incorporated. I've been in the industry for almost over 35 years now, since 1986. And my specialization is in material science and surface engineering.
So, what first drew you to material science, and when did you realize that you really want to focus on surface engineering?
Interesting question. It dates back to 1985 when I was doing my master's in physics back in India, and I was actually performing some physics experiments of crystal growth, and it uses a technique called a Czechoslovakia method to grow crystals, and this is a traditional way of growing single crystals. So I was trying to grow some silicon uh, single crystal uh, rod, and basically you put a seed in there, and there's a process of heat and pressure which helps grow the single crystal. So that process actually showed me how you can actually grow some material out of a seed, and that kind of made me inquisitive about material science.
So, can you walk us through your journey from your PhD to becoming the director of engineering at the Plasma Technology?
Yeah, sure. My PhD, I actually uh, started my PhD back in '86. Then I stopped doing my PhD for a while, and then came back again to do PhD in material science. Interestingly, I started doing PhD in plasma physics and trying to understand electron densities during the 85, 86, 86, 87 time frame. But it didn't interest me much at that time, so I switched my career altogether into what was back then mostly in marketing and sales, in fact, of electronic materials, electronic computers. Back then in 85 was in the primitive stage. And then later on, I went back to do my PhD. But the years I spent in doing marketing actually taught me a lot of how I interacted with people, and how to, in fact, talk to people and relate to people. So that kind of was also helpful. And then I started my PhD in material science, and I worked on materials which were hard in nature, basically close to diamond and diamond-like materials. So that was my interest, and that's what I started. I also parallelly was a full-time professor at that time, teaching material science and physics to the undergrad students. And I used to actually show them how experiments are done back then while I was teaching, and I would do my part-time PhD at the same time. So it was a very hectic time for me, but it also taught me how to uh, time manage a lot of stuff and work on multitasking uh, at the time. So that was when I was working on multiple projects and doing a lot of work on material science. I finished my PhD around 1994 time frame, and that's when I actually switched over to industry and started working as a senior scientist and engineering manager at a company called as Multi-Arc that was in India. And I had a collaboration at that time with a New Jersey-based company, which was Multi-Arc New Jersey. And so we were working together on developing a lot of different materials, coatings for industrial applications. And we actually did a lot of commercial work at that time with a lot of automotive industries back then. And in 2000, when I moved to United States, because I had so many connections with the industry people over here, and I would come to San Diego for a lot of conferences at that time from India. I actually was introduced to a lot of brilliant scientists and engineers, and one of them actually hired me in Ohio, and I actually transitioned straight for industrial work as a senior manager in a company in Dayton, Ohio. And I was working with Wright Pat Air Force Base at that time, developing a lot of hard materials and coatings for their aerospace applications. So there was a transition from automotive to aerospace at that time. And then in 2003, I got an opportunity from it came out of blue from a headhunter who got introduced to me through my other connections in industry, and they actually offered me a job as director of engineering at Plasma Technology. So since 2003, 23 years I'm here.
So, what were some of the biggest challenges that you faced breaking into the aerospace industry?
Aerospace industry is very different in terms of quality requirements, and I came from an automotive background initially. So it's all land based, so everything runs on ground with automotive. And when you switch over from ground to aerospace, you're flying in air, you're going against gravity, and the challenges are totally different. And you have to be very, very quality conscious, because nothing can go wrong in terms of the product you develop. And the quality was of paramount importance at that time. So that is the biggest challenge, I would say, when you transition from something which is more stable, like a ground based vehicle or an instrument, to something which flies in air.
I
Make
see.
sense?
Yeah, yeah, yeah.
All right.
Yeah. That's so like unique and like interesting. Um,
Yeah.
for the people who may not know, what exactly is surface engineering and why does it matter?
Basically, surface engineering is tailoring of surfaces. So you basically look at surface engineering as something which counters wear, corrosion, erosion, and various other factors. So something which rubs against each other is going to wear. But if you want to, and so if there's one surface which is softer than the other surface, then the softer surface is going to wear against the harder surface. So in order to protect the soft surface from wearing, you put a thin layer or tailor the soft surface in such a way that it makes it harder, so that it won't wear much. And this is very important when you are dealing with materials like titanium, which is an aerospace based material, which is very expensive. And you want to tailor the surface of titanium so that now you have a lightweight material which is good for airborne surfaces, and then it also won't wear. So the surface engineering and coatings are necessary to protect the more expensive and costly equipment you're dealing with, so that it gives them more life. And it's in a way, it's called as kind of treated as an insurance in a way. So the insurance gives you that extra protection, right? So that's what it is.
I see. So, how do the materials on a spacecraft actually affect its aerodynamics and performance in flight?
So basically, you're looking at the uh, spacecraft materials which are lightweight, right? And so basically, what you're looking at, uh, materials or coatings which are compatible to uh, outer space and work in vacuum. So they protect the surface which they are getting experience to. So whatever works in under atmosphere won't work the same way in vacuum when you're in outer space. So the materials have to be tailored. For example, lubrication, for example. So when you work with the materials on ground, uh, on earth, and you're lowering the friction, or giving by giving better lubrication, those are oil based or grease based kind of lubricants. those things won't work in space just because of the way the chemistry works. In vacuum, you cannot have something which is going to vaporize. So in that case, you have to now come up with lubricants which are dry, won't have any oil or any liquid form. So that's so there's lubricants called as moly disulfide or tungsten disulfide, kind of dry lubricants which work effectively in space. Also, the surfaces have to be tailored. For example, SpaceX shuttles which re-enter back into Earth, um, when they are entering back into the Earth, they're experience the extreme friction, because when it's re-entering, it's interacting with atmosphere at an extremely high velocity, and that leads it to give a lot of friction with air particles, and uh, that generates extreme heat, and that can actually melt any material or surface, any metal, for example. Even if it's very hard, even if it's very strong, it can melt because of the extreme heat, which can be 4 5,000 degrees Fahrenheit. So basically what surface engineering does is give you can do a protective thermal barrier layer onto the surface, or there are specialized tiles like silicon carbide based tiles, which can now protect the base material from getting exposed to that high temperature. So basically that's probably in a nutshell, to give you an idea of what how the surface engineering can help aerospace.
That makes sense. So
Yeah,
can you
I
now
hope I'm making sense.
no, that
It's
makes
my
sense. Like it's
okay.
helping me understand like the importance of like materials and like how it
Right,
works. Yeah.
right. Yes.
So can you now explain like PVD and CVD coatings? Like we're hearing them for the first time because like me personally, I don't know what they are either.
Yeah, you're switching gears here. Surface engineering is a vast field. PVD CVD is a small subset of surface engineering. PVD, which stands for physical vapor deposition, obviously tells you deposition, meaning coatings, and CVD is chemical vapor deposition. In the name itself, you can see chemistry is involved when it comes to CVD, and it's a physical process when it comes to PVD. Uh, they can both work under vacuum. A vacuum is used to minimize any interaction between particles so that they don't have any hindrance in depositing onto the surface. Both are deposition processes, so you have to understand they are coating processes, and they're trying to coat surfaces with a variety of protection materials. They could be hard coatings, they could be soft coatings, depending upon the application. But a physical vapor deposition is mostly done under vacuum, and it uses materials which are in the form of a physical target, and they can be either deposited in the form of a sputtered physically transported material to form a layer on a surface, or it can be vaporized. So you can use like a thermal energy to vaporize some material like metals to form layers. You can convert that metal into a form of a plasma and interact with reactive gas to form reactive gas interacted material. So, for example, you evaporate titanium, you put nitrogen, you form a titanium nitride layer, which is extremely hard. Uh, Similarly, you can actually just lift off uh, carbon in a special atmosphere of hydrogen and form an allotrope of carbon in a form of a thin layer, which is extremely hard and called as diamond-like carbon coatings. So they are all line of sight processes, mostly PVDs or physical vapor deposition. Whereas in a chemical vapor deposition, now you're involving some sort of chemistry in the form of gases or liquids, and they are actually done at extremely high temperatures so that the gases or liquids can be broken down into their elemental forms, and then they can be deposited into coating. A chemical vapor deposition need not be line of sight, and that's an advantage with CVD, is that when you are coating something which is not seen directly. So, for example, you're trying to put a layer inside a tube, or something which you are trying to do a three-dimensional surface, then you end up doing a CVD process. So, the distinction is the CVD can be in vacuum or it can be done in atmosphere. A PVD is primarily done under vacuum. PVD is line of sight. CVD, it could be non-line of sight or line of sight, depending upon what process is used, but they both generate uh, hard coatings or materials which are resistant to corrosion, erosion, wear. CVD coatings can be extremely thick. PVD are typically very thin. So depending upon what application you do, you're trying to generate integrated circuits. Then you use a PVD technique. Well, it's a very elaborate process, but in a nutshell, it can be done in a fab to generate multi-layer coatings, etched and form devices. Very very thin layers, two thicker layers which are done in cutting tools, like you might have seen in a hardware store. You see these golden yellow colored tools which are titanium nitride coated. They're all done in PVD. They could be also done in CVD techniques, using CVD processes on cutting tools, like you might have seen those triangular diamond cutting tools, or carbide cutting tools. They are all CVD, titanium nitride coated, and there is thousands of different coatings which go in there.
That makes so much more sense now because like
Thanks.
a lot of when I was reading like your description, this came up on a lot and I was wondering like what it really means. And
Right, right.
it makes
It
more
can it
sense now.
Yeah, it can get very complicated because there is so many different words used in
Yeah.
there, and if you're not accustomed to understanding or using those terminologies on a day-to-day basis, it could be confusing to you. Yeah.
Yeah, but that was like really clear and like simple explanation.
Yeah, I tried to keep it as simple as I could.
No, that was.
Okay.
So, how do these coatings on a spacecraft like really help them survive extreme heat or pressure or friction during launch or re-entry?
Yeah, so basically these coatings, like I said, space applications are different compared to automotive applications. So when you apply these materials in the form of coatings, thin or little thick coatings, so different techniques are used. It's not just PVD, CVD. Uh, there's also thermal spray techniques which are used to deposit extremely thick coatings. A lot of the space applications or even aircraft applications, like for example the engines, the blades in the engines are all coated. They are extremely high temperature, hard materials, which are nickel based alloys, which are the blades in the turbine engines. uh, they are all coated. If you don't coat those blades, they will melt away. So it's extremely high temperature for the turbo engines. So the coatings are specifically developed for different applications. So the cold section, the turbine engine is broadly divided into a cold section and a hot section. So the cold section of the turbine engine basically gets coatings which are applied so that the blade edges are called as a leading edge of the blade is protected. So in the cold section of the engine, the blades can experience a lot of erosion issues because of the particulates which are bombarding. So the fan blade rotates at extremely high speed, revolutions, and basically it can actually suck in a lot of dust particles, and depends on where which atmosphere it is going in. If it's in a desert like atmosphere, you might actually get sand ingested into the turbine engine. So the leading edge of the cold section of the suction side of the turbine has to be protected with hard coatings on the leading edges. Whereas as the air goes into hot section and expands to provide that extra thrust for the aircraft to fly or the spacecraft to fly, at that point you end up getting the blades which are slightly smaller in size at that point, and they go keep on changing the size, but they all get coated with a thermal barrier coating, so that they resist very extremely high temperatures and cycling of the temperature cycling onto into the turbine section. So that's one example. Re-entry vehicles like spacecrafts, you might have seen the SpaceX shuttle re-enters back into and then lands onto the ocean, uh, which is a reusable rocket. Basically has thrusters in it and stabilizers in it, and the stabilizers open up to stabilize the re-entry of the spacecraft. At that point, those are experiencing extremely high temperature because they're resisting they're trying to balance the spacecraft, so they are actually resisting a lot of air, atmospheric air and particulates, so they experience a lot of heat, so the thermal barrier coatings are applied onto that. There are thousands of examples where protection is needed for turbine engines into the aerospace applications. Similarly, turbines used in land-based power generators also go through extreme temperatures, and they also need to be protected with coatings. So coatings is all pervasive. It is everywhere in every kind of application you use. There's a surface layer which is protecting it. A wood surface needs to be protected with varnish and paint for protecting it from wearing down due to weathering. House is painted, which is another protection, which is a coating basically. So you can't escape coating.
I see. No, this is so much like new information that I wasn't familiar with before, and like I'm getting a lot of new insight on like a topic that I didn't really think was important or didn't really know about it.
Yeah, yeah.
So yeah. So what does a typical day look like in your life as an engineering director?
Oh, basically, I'm managing a lot of different new projects, which is new development of products and materials. I also support the production team in solving some issues, and also working on some internal research and development work where I develop new products and new materials. So it's a mix of different tasks. I lead different teams in new products, and I deal in regular production too. So we work with a lot of different companies like Boeing, Pratt and Whitney, GE, Rolls Royce. All the nice fancy names you hear. But we work with all these aircraft manufacturing companies. So there's a lot of always challenges. So typical day would start with planning for the day as I enter into the workplace, and it does start much before that too, because the brain doesn't stop working, right? So you start working towards what the plan is for the day, and then come in, and then if I have meetings planned, then I schedule those out. They're already scheduled, of course, but I had to plan ahead of time what I need to speak, what I need to talk, and then there are various customer requirements which have to be met. So I work closely with the QC department as well as production team. So for most part of the mornings is more active in terms of planning and what kind of work needs to be executed on that day, and then meet with the teams and plan up the work schedule for them. And if there are some issues in terms of management as well as in terms of technical needs, then we address those ones. And then afternoons are mostly spent on working on new projects and developments. And then I also uh, try to read uh, uh, on the new technologies and the new developments in the industry. So that is scheduled for later part of the day.
So how much of your work is like hands-on or in the lab versus like design and research or like leading a team?
Yeah, good question. A lot of people, I don't know today's word, um, think that you can mostly manage everything sitting behind the screen on a computer, and communicate with people and get work done, or work on your projects sitting there. Uh, to some extent true, uh, but most of the times, unless you have worked with your own hands and solved problems and done work on projects, especially for an engineer, uh, and a production engineer for that matter, specifically in the area of chemical engineering, mechanical engineering, electrical engineering, material science. um, I'm not talking about the people who are into the much fascinating AI and in the computer science side, but most others, for them, hands-on work is what actually teaches them about how to tackle problems. So I'm a hands-on guy, and I love to do work. If I'm doing coatings or spray work, I try to do it on my own. Also, when I'm trying to develop some new processes, I go through the steps and I run those, um, and then hand it over to the operator to execute it, and then do the production team to implement it. So that's how I do it. I don't know, a lot of managers don't leave their office and they just sit behind the screen and try to manage stuff, but I'm particularly feel that a mechanical engineer or a metallurgy engineer or a material science materials engineer should be hands on.
Yeah, because I feel like my generation, like we work so much on computer and we don't really get a lot of experience like with hands-on. And I do believe like getting hands-on experience, especially like if you're going in engineering, is really crucial because that's how you will learn like the technique.
Yeah, absolutely. You don't get your hands dirty. It's hard for you to understand what the team on the shop floor is experiencing.
Yeah.
And so when they have a problem and you don't know how to address that problem, as a manager, you don't look good in their face. So
Yeah.
basically, you should know how to solve the problem for them. They are experienced, they do that every day in day out, and there are people who work for 30, 40 years on a product line, and they know in and out about that material. So many times, an engineer, when you work with them, you learn a lot, even though you are highly qualified. Like I'm a PhD, but I work with some of the shop floor workers or operators who have been working for 30, 40, 50 years, and they know in and out about the machinery and the material they're dealing with. That their insight is totally different than what you have learned through your books and your education. So you need to work with your hands so that you understand what the issues are, and then maybe apply your knowledge to solve the problems.
So now moving on to questions that like the audience may have, what advice would you give to high school students interested in material science or just engineering in general?
Basically, I would say, for students, uh, you should, I feel, stay curious, ask questions, uh, and be ready to work with your hands and experiment. Unless you mess around, make mistakes, you won't understand what's going on. So, especially in material science, where the development is happening very rapidly, and you cannot, like coatings. I'm doing coatings. I'm more expertise in coatings and surface engineering, but even for that matter, most of the materials are, most of the applications are material driven. So you cannot uh, achieve anything until you venture on to learn, take risk, work on what excites you most. And you should be curious. It should make it interesting. If it's mundane work, then you may not have much interest in it for too long. Probably pays you good money when you're working in the industry, but it may not interest you. Maybe you just work for the sake of earning money. So that should not be the motto. I think it should be primary goal to earn money, of course, but at the same time you should be curious. So like for example, materials, for example, I'm saying, like, they encompass pretty much everything in all walks of life. Maybe it's a Tesla battery, for example. It's all material driven, the chemistry, but there's also materials which control the operation of the battery. Same thing with rockets, SpaceX or Blue Origin rockets, or a Boeing 777 Max engine is all materials and engineering. Um, Unless you have those, you tackle those and understand and be curious about how things work, you won't get curious about it and interested in it. So I would advise, be curious.
Yeah. So lastly, addressing like a future question, where do you see aerospace material technology heading in the next 10 or 20 years?
Wow, that's a loaded question. There is a lot happening in terms of space exploration. As you might have read, or heard, there's a lot of interest in going to Mars. Now you're looking at millions of miles away, taking not just few days but years to reach. Um, Especially when you're designing any spacecraft or launch vehicle which is supposed to reach such extreme distances and meet with extreme conditions, the materials which you design have to be uh, uh, have to be evaluated and made sure that they will meet those requirements. And it's not an easy task. So you have to simulate a lot of those atmospheres on Earth and experiment with materials which can tackle those situations. So those are the challenges which are looking at. Going back to moon is not the same as they did way back during 60s. So you are looking at new challenges, um, which have to be encountered. In fact, we are working with closely working with the NASA project, where we are working on surface engineering moon dust excavator. There's a lot of challenges which are there in terms of simulating that into on here. So we actually uh, generate moon dust, which similar chemistry, morphology, and then we experiment with what kind of surface engineering has to be done on an excavator so that it can uh, sustain that wear, erosion, corrosion issues, which might actually experience over there. So those are the challenges you're looking at. So basically, you have to be prepared to and then also be able to simulate those kind of situations on Earth over here, so that you know what you're generating or what you're manufacturing will meet those challenges.
This was such an interesting conversation, and I learned so much about like material science, surface engineering, and the important role like coding has in spacecraft and environments. And
Yeah,
hearing about your journey in the aerospace industry and your experience was really inspiring, and I hope our audience also felt inspired. So thank you so much for taking your time to
thank
share
you.
experiences, insights, and advice with us today.
Absolutely, absolutely. Yeah, materials science, surface engineering fascinates me a lot. With
Yes.
the advent of artificial intelligence, it has become more interesting now to make use of the AI tools to explore new generation materials, certain combinations or alloy formations which actually were never thought possible are possible now because of AI tools. So it's becoming very interesting, a very interesting field.
Yes, for
There's a
sure.
lot to learn. There's a
Yeah.
lot to learn, a lot to explore. It's a very fascinating area.
Thank you so much for coming.
Thank you. Thanks, Amy, and all the best. Thank
Thank
you.
you. Thank you to everyone who joined us for today's episode. I hope you learned something new and felt just as inspired as I did. Make sure to join me next time for another conversation that inspires curiosity and learning. Till then, explore, engineer, and elevate. See you next time.